Okay, let's take a look here at a new chapter. So last chapter, chapter 3, it was all about polynomials, and we were factoring polynomials, um, and finding zeros of polynomials, and then drawing graphs, right? Drawing graphs of polynomials. So now we're going to kind of take it a half a step further, maybe a little more than a half a step, maybe 3/4 of a step further, and we're going to talk about rational functions. 4.1. So yeah, the whole chapter is about rational functions, and it's kind of going to be like the last chapter, where we kind of just snowballed a set of tools that we were kind of painting little portions of the picture, and then at the end we did the whole picture, right? We did everything all at once. We're going to kind of do the same thing with rational functions. So maybe we can sort of put that in the back of our head. It's like, we're putting together little tiny pieces one by one by one, and we should think about the big picture as we're going along. And maybe I'll mention that, but the homework assignments are going to be pretty focused, do this exact task, stuff like that. So anyway, let's get on with it. So yeah, we got a definition here, which ought to be familiar, right? Ratio of polynomial functions. So a rational function is a function of the form where we've got some rational function divided by a rational function. So, right, we can write it maybe if our function is called f. Make that look better. If our function is called f, said it was going to look better and then it didn't, we're going to be able to write it as a quotient, right, or a fraction. So we've got some numerator that is a polynomial and some denominator that is a polynomial. So the big thing we recall from fractions is that we cannot have zeros in our denominators. So this thing right here can't be 0, right? Okay, so when we have a domain and we wrote it like this, right? Our domain is going to be the set of all x values, so the set of all x, so that we can't have a 0 denominator. So q of x not 0. So what we're going to do to find domains, and we've already done this, right? We've done this before. We need this stuff in the denominator needs to be non-zero. So we find out, that looks pretty terrible, non-zero. So what we do is we just find the x value that makes it 0, right? We set x plus 1 equal to 0, and we can solve this one. We would have x equal -1. So this is going to be our domain restriction. So our domain, we could write this as the set of all x, so that x is not the value that we just found, right? So yeah, x is not -1. Okay, cool. So that one wasn't so tough. And we can write this as an interval as well. It might help us to draw a number line, right? Here's -1 on a number line. And we don't want that value, but we want everything else to the right. And we want everything else to the left. And we would just find, the union of those two intervals. So left-hand side, we would have -infinity, and we would go all the way to 1, negative. We don't include -1, and then we want everything to the right of -1. Okay, cool. So we can write it in either way. Yeah, set builder notation, or we can use interval notation. Okay, so the last part about this was that we had to write it in this form, P over Q, and simplify, right? Do we remember what simplify means? I hope we do. Like 4 over 8, this is not simplified, right? Because we know that that's what, 2 times 2 over 2 times 4. Well, we could just write 4 over 2 times 4, right? 4 over 2 times 4. And then, hey, we got a common factor. Those guys both cancel out and become 1s in the factorization. So I got 1 left in the numerator, and then 2 times 1 would be 2 in the denominator. Right, we're going to do the same thing with fractions, and we have done the same thing with fractions. So we try to factor, and if we can't, well, then that's it. And there's no common factor, no common factor in this case. So it's already simplified here. We'll have one that we can simplify here in a minute. Okay, good. We have another one. We want to find the domain. So yeah, really we want to just take it right as it's given find any denominator, and now this thing can't be 0. Right, so we find the value that makes it 0, and we throw it out, right? So I can't have this value x such that x can't be -1. So that's our domain, and we could write it as an interval as well, right? And we can, we can do that real fast. To -1 union -1 to infinity. Okay, but now we have to write it in the form p over q. So I want one polynomial over another polynomial. Right, that's what we want, but that's, oh yeah, right, all we have to do is just add the fraction. So we know how to add fractions, right? We need a common denominator. So just like if we're adding maybe, I don't know, 3/4 plus 2 ninths maybe. Well, let me make that a different one. Let's have it be a 6. Let's have that be a 1. Okay, so if just like over here on the right where I want to do it with fractions, I need a common denominator, right? We want the least common denominator. So I know that this is 2 times 3, and I know that this is 2 squared, right? A factorization. So the least common denominator is going to be the smallest number that both of these numbers divide evenly into. So it's going to need a 2 squared, and it's going to need a 3, right? So that's the least common denominator. We take this each individual factor and raise it to the highest number that appears here. So our LCD in this case is 2 squared times 3, right? So that's 12, right? So we just have to multiply by whatever we need to get to 12. So here it's 2 over 2, and here it's 3 over 3. And we know how to add fractions. We've been doing this for a while. Part of the reason why we're asking you not to use calculators is so that we can get used to this, and doing adding fractions with integers makes that stuff a whole lot easier, right? Because I know that I need a common denominator. Well, my denominator here is 1. So if I'm going to multiply by something that's going to get me my common denominator right there, well, that's all I need to do, right? X plus 1 over x plus 1. And this guy, we don't have to multiply by anything, right? So carrying this operation out, we can do this. We multiply, right? 2x plus 1 over x plus 1 minus 3 over x plus 1. But yeah, now we know that when we add fractions, we keep the common denominator and combine the numerators. So here we would have 2x plus 1 minus 3 over x plus 1. And we can simplify that. Right, we're going to have 2x, minus 2 over x plus 1. Okay, so now we try to factor it and see if we can simplify it, right? So we can try to factor this. Looks like a 2 will come out of that top, but that's not going to do anything for us, right? Because these are now, that guy's a minus, that guy's a plus. So these things are not common factors, and we can't cancel anything out. So it just stays there. And maybe notice that we can still find the domain right here, right? The x equal -1 is still restricted. Can't have that. Okay, cool. So we found the domain and we wrote it as a polynomial over a polynomial. Great. Okay, we can do the same thing with this one. Kind of just a general tip here is that we might want to factor everything just right away and kind of get used to just factoring everything right away. So if there's something that jumps out that we can just cancel before we even start, we might want to think about doing that. But we shouldn't cancel it right away, and we'll get to that here in a second. Anyway, let's just perform the task at hand here. So we want the domain, right? So we want all the values so that any denominator is not 0. So that thing can't be 0, right? So we can't have x squared minus 1 equals 0. So we can solve this really quickly. We probably already know that the solutions are plus or minus 1, right? We can find these by factoring, right? Because we know that that's the difference of 2 squares. And then we use that 0 product property, right? Okay, so we got x can't be this number. Well, there's another denominator hidden here, right? That is a denominator. When we have a division symbol here, here's what this means. We can rewrite this as 2x squared minus 1 over x squared minus 1 over 3x minus 2, right? Because this is what we're dividing by. So this main division bar guy, that's what this thing means, right? That's the main division going on here. So we also can't have this thing equal to 0. So that can't happen, right? So we just go ahead and find the things that make it. Okay, so when we're solving where are we here? When we're solving a rational equation, these always work out the same way. All we have to do is find where the numerator is 0. And here's why that is. Whoops, that was a 3x minus 2. Okay, so our first step here is going to be to get rid of the fractions. Well, since we've already noted that we can't have plus or minus -1, we know that this denominator is not going to be 0. So that means that we can multiply both sides of the equation by it. And that's still going to give us a true statement, or it's going to give us an equivalent statement. So we're just multiplying both sides by this denominator here. And it's going to, cancel itself out, right? Cancel, cancel. And we're left with 3x minus 2 equal, well, 0 times anything is always just 0, so we got 0. Okay, we can solve this one pretty quick here, right? We would have x equal, we would add the 2 divided by the 3. So we also can't have 2/3. So writing our domain, we have the set of all x values so that x can't be -1, it can't be 1, and it can't be 2/3. So we can't have those 3 values. We might want to write that with an interval. So I don't know if we have trouble with this, and it's okay if you do, draw a picture. So I know that they're arranged in this way, right? I know we can't have those values. I want everything over here. I want everything in here. I want everything in here, everything over here. So I want everything except for these numbers, right? So we got -infinity all the way to -1. Don't include it. And then we want -1 all the way to 2/3. Don't include that. Then I want 2/3 all the way up to 1. And don't include 1. And then 1 to infinity. So we take out just those 3 numbers. Okay, great. So we got the domain now. And now we want to do that simplified part. So here was our original function, right? We know that when we divide by a fraction, what we do is we multiply by the reciprocal of what we're trying to divide by. You remember this? So instead of dividing by that number, we multiply by its reciprocal. That ought not be a 2. So that we're getting the reciprocal of that guy. So 3x minus 2, right? The numerator and the denominator just flip. Okay, and now, well, something convenient's going to happen here, right? We see that we've got common factors, right? X squared minus 1 goes away here. And then we can write it as 2x squared minus 1 over 3x minus 2. Excuse me. Okay, so something to notice here. Well, I guess we should say whether or not we're done. So we can kind of see a couple of steps ahead, at least with the numerator here. If we're going to factor this into 2 linear factors, we're going to have a square root involved somewhere, right? Because we're going to, if we factored that as 2 times x squared minus 1/2, we can factor that piece as a difference of 2 squares, just like we did in the past. In the past, right? The last couple sections. So anyway, we can see ahead 1 step or 2 steps to see that, that's not going to factor with this guy, right? There's not going to be a common factor. So anyway, we're finished here because nothing else is going to cancel out. All right. Something to notice is that our domain here had these restrictions. Our original function had these domain restrictions, right? We couldn't have -1, 1, or 2/3. And we could write it as an interval too, but that's not quite the point right now. So our original function had this as a domain, and we just showed that our original function is equivalent to this one. So there's a problem here, right? And I hope we see it. These two numbers are perfectly fine to put in here, right? I can put a -1 in for x here, and I can put a 1 in for x here. And we can point to the part that made this happen and caused our concern. And it was right here where we canceled that 0 out, right? So once we canceled that factor, it wasn't a 0 anymore. And it's going to deceivingly be not in the domain of our function that looks like this. What that's going to represent is going to be a hole in the graph. And so what we're saying is the original function behaves exactly like this one, except for where x is plus or minus 1, right? So, well, it's going to look like this graph everywhere except here, and that's just one single point. So we'll just take that point out of the graph. We'll have a better example for this in a second, but let's move on here to the next idea. Okay, vertical asymptote. Let's draw a picture. So the line x equals c, we know that that's a vertical line, right, from our past section. So if I got a line, let's draw a line. Here's the line x equals c. Okay, and it's a dashed line. And it's at the, goes through this point right here. We know that that's c comma 0, right? Okay, so this is called a vertical asymptote. If the graph, or of the graph of a function y equals f of x, if as x goes, so what this means is approaches c from the left. Right, when we put that little minus sign up there, we mean we're approaching c from the left-hand side. So we're going towards c with our x values, not necessarily what the function is doing. The function's not going toward that point, but as we move our x values toward that point, if the function goes toward infinity, excuse me, if the function goes toward infinity, so that means if the function gets really, really, really big as I approach my x value, x equals c, right? If it gets really, really big, or if that function gets really, really small or really, really low on the graph, right? It goes down, down, down forever. We call this a vertical asymptote. The line x equals c is a vertical asymptote here. Okay, so usually we have an okay idea of what an asymptote is, because we've probably seen it before in previous coursework. Okay, so asymptotes. So something that we should think about is y equal 1 over x, because this is the one we're intimately familiar with. So we know what this picture looks like, and if we need to plot some points to draw the graph again, plot some points, but we ought to know what this looks like from our transformation section, right? And observe that the line here, x equals 0, is an asymptote, right? A vertical asymptote. So we're just kind of connecting, right? That's x equals 0 is a vertical asymptote. Yeah, vertical asymptote. And notice where that happens, right? X equals 0 is a 0 of the denominator. So what we can kind of take away from this, putting together what we already know, is it sure looks like if I have a 0 of a denominator, that's going to be a vertical asymptote. That's what it kind of looks like. And think about this with transformations as well, right? If I wanted to draw y equal 1 over x minus 1, that's going to move this graph that we drew on the right, it's going to move it to the right 1 unit, isn't it? Because we're just subtracting from the x value. Well, it moves everything over 1 unit, including that asymptote. So it's going to look, like this. So x equal 1 for this graph is a 0 of the denominator. So notice this. So really, we're just going to be looking for zeros of denominators eventually. Okay, so good. Here we go. let's put this idea together here. Location of vertical asymptotes and holes. Let me get room up here. Okay, so let's suppose that R is a rational function that can be written as a polynomial over another polynomial where P and Q have no common zeros. Okay, let's C be a real number which is not in the domain of R. Okay, so that means it has to be in a zero of the denominator, right? So let's maybe write one of these out here and kind of look at what's happening. So how about, I'm just moving that all over the place. Let's have x minus 2 in the numerator, and let's have x times x minus 2 in the denominator. So let's pretend like let's pretend like we haven't done anything yet here, and let's just observe maybe say what the domain is here. So the domain, we know that the denominator can't be 0, right? So this is the set of all x, so that denominator can't be 0. So we can't have 0 and we can't have 2, right? Okay, so we would probably reduce this, and if we do, we see that if we treat that whole numerator as a factor, if we treat this whole numerator like a factor, it cancels out with that one. So we have 1 over x. So this graph looks just like the graph of 1 over x, except the things in our domain, right? Whoops, x can't be these things, excuse me. Hopefully we noticed that. So our domain restriction 2 got canceled out. So what the graph is going to look like, well, it's going to look exactly like the graph of this one, which we drew above, and we know what that looks like, except at x equal 2, right? So at x equal 2, we have a domain restriction, and it's a hole in the graph. Because our picture is going to look just like that reciprocal function, that 1 over x. So this is the point 1, 1. We know that's there, and we know it's going to go up here. And we know that it's got the point negative 1, negative 1. We know that's on there, and we know that it looks like this. But then I've got x equal 2 can't be there, right? So that means, if I put a 2 in there, we would get 1/2. So the graph would look around there about like this, where that's 2 comma 1/2, and we got, the picture's just got a hole in it. It looks just like the reciprocal function, but it's just got a hole in it there. So this is a relatively simple-ish example before we say what the mathy stuff is, right? So, okay, let's compare what we did. So if we've got a rational function that can be written as P over Q, where P and Q have no zeros. Okay, so we had the rational function. It was right there. It was what we started with, x minus 2 over x times x minus 2. That's what we started with. And it can be written as P over Q where they don't have any common zeros, right? Well, there it is. So we factored out, canceled out the common factor, and we did that. Okay, so now let C be a real number which is not in the domain. Okay, we made a list. Right away, we made a list. We already have that list. Okay, if Q of C is not 0, so what this is saying, check it out. If we put 0 in this, 1 over 0, that's not defined, so that's still not in the domain. If I put 2 into this, though, I get 1/2, and that's not 0, right? Which is the case we're in here above. So this means if we canceled a common factor, it's not in the denominator anymore. Okay, so if that's true, then we're going to have a hole in the graph, which is what we just did right here with our 2 comma 1/2. Okay, so if Q of C is still a 0, the domain restriction remains. So yeah, and that's what we saw here, right? The domain restriction was still there, so that was an asymptote, right? And it would look like that reciprocal function. Okay, so hopefully that example helped make the hole in the graph slash vertical asymptote thing make a little more sense here. Let's look at a few more examples. So find the vertical asymptotes or holes in the graph. So yeah, word to the wise here, we just want to try to factor everything first, and that's just going to help us out. So we can write this as 2x over, what is this going to be, x plus or minus square root of 3? Because this is that difference of squares formula, right? Or the factoring rule, right? Okay, so we can see, hey, I factored everything. There's no common factors, so that's fine. We can list our domain restrictions. Or maybe I can just write what the domain is, right? So set of all x so that x can't be plus or minus square root of 3. Okay, so we found our domain restrictions. That is wonderful. There they are. And if we really want to, we can write this as an interval. Let's not right now because that's not really the point. Okay, so now we go look back at our function and we say, hey, can I cancel anything? Well, we can't cancel anything. So that means we're in that form that we had in the nice theorem here, right? We have it in reduced form. So if it's reduced, and these domain restrictions still remain, these are vertical asymptotes. So we have vertical asymptotes at x equal square root of 3 and x equal negative square root of 3. So these are vertical lines, right? We're giving equations for vertical lines. Okay, so we found vertical asymptotes and there are no holes. And we know this because we didn't cancel anything. Okay, and that's all we really wanted to do with this example. But let's try to think about things we already know and try to start halfway putting these pictures together already, because that's kind of where we're headed. And we should be thinking of these things as we're doing these tasks. So here's square root of 3, here's negative square root of 3. We've got asymptotes here, right? They look like this. All right. What else can we put on this graph? Maybe I don't know, points that jump out ought to be intercepts, right? So any x or y intercept. So what's going to happen when we put f of 0 in there? And that's going to be our y-intercept, isn't it? So if we do that, we see that it's just going to be 0 right away, right? We've got in the numerator 2 times 0, and that's just 0. And then I've got 0 minus 3, so that's 0 over minus 3, so that's 0, right? So we have the point 0, 0 is on our graph. Well, now I know I've got vertical asymptote here, vertical asymptote here. So I know that after I'm leaving this point right there, we're either going to have to go up or we're going to have to go down. One of those things is going to have to happen. We're going to either go up or we're going to go down here. One of those things is going to happen, right? And guess how we're going to find out? Test points. So we can pick a point here, and go from there and use our test points to sort of draw the picture. But I don't want to get too far afield of the actual point here. So we're finding vertical asymptotes and we're finding holes in the graph. And we should be keeping in mind what it's going to start to look like. But we're finished with this example. We found that there were no holes. We found the vertical asymptotes. So let's do the next one. All right, so yeah, we're finding vertical asymptotes and we're finding holes in the graph. So what we want, well, what we will need, as we've seen, is to factor everything. So the numerator here, what we want two things that multiply to be negative 6, that add to be negative 1. So their difference is going to be 1. So it looks like 2 and 3 are going to work. X, minus 3, x plus 2. Okay, and we can check that to, multiply it back out. And then this guy, that's the difference of two squares again, plus 3. Okay, so we list our domain. This is the set of all x so that x is not what? We can't have denominator be 0, so that means that it can't be 3 or negative 3. So we can write that plus or minus 3. Okay, and then we would reduce it, right? We want to reduce this thing, and we see that we have common factors, right? That x minus 3 is in common. So now it's x plus 2 over x plus 3. and now this is reduced. All right. So now we need to go and check and see if these domain restrictions still remain. So one way we could do that is, yeah, we could plug them in there and we could say, hey, does it give you 0 or does it not give you 0? Another way to think about this is just the thing we canceled, right? We canceled out the factor that made it so x could not be 3, right? So we can still have x equal 3 in this one, the reduced one. So we want to not have that, right? So we canceled x minus 3. So x equals 3 has a hole in the graph. Okay, so our other one, our remaining domain restriction, is a vertical asymptote. So this is x equal -3, right? Because x equal -3 is still domain restriction. All right, so we got a vertical asymptote, and we've got a hole in the graph where x equals 3. So a natural question here might be, what's the y coordinate? So we just find the y coordinate like we do for any other point ever, right? We just plug it into the function. So if we plug it into the original function, it's not going to work, right? But the fact that we canceled it out is going to make it so it does work in the reduced one. So we find the y coordinate by evaluating f of 3 in the reduced function. I want to kind of put that in a little box here too, separate from that. Okay, so we're finding the y coordinate by finding f of 3 in the reduced function, which we can do, right? F of 3 in the reduced one, we would have 3 plus 2 over 3 plus 3, right? That reduced function's right up there. We put 3 in there, so that would be 5 over 6. So that tells us that there's a hole at the point 3, 5, 6. So we've got a vertical asymptote at x equal -3. That's a vertical line. And we've got a hole in the graph where x equals 3, and we found that y value by just evaluating that in the function. All right, cool. All right, one more here. We got part C. So we're finding vertical asymptotes, we're finding holes in the graph. So we've seen those other ones, we're just going to have to factor everything right away. Well, we're going to have to factor everything in the long run, so we might as well just do it right away, right? Okay, so that numerator, we've seen that before. So this is x minus 3, x plus 2, okay? And then the denominator, that looks like x plus 2, x plus 2. Okay, so our domain here is the set of all x so that the denominator is not 0. Well, the only thing that's going to make the denominator 0 in this case is -2. All right, so there's where we start. And now we can cancel our common factors because we want to write it as a reduced fraction, right? So this is x minus 3 over x plus 2. Okay, so now this domain restriction remains, right? It's true that we canceled it out, but that domain restriction is still there, right? We still can't have x equal -2. So, I mean, just fitting it specifically into the statement of this nice theorem, this would be in the case where the denominator evaluated at that point is, it's still 0, right? So anyway, this says that x equal -2 is a vertical asymptote. Okay, and we're done. Super, so that's vertical asymptotes and holes in the graph. We'll see more examples with holes in the graph. Those are usually troublesome for students, so we'll look at another one, I'm sure. Okay, now we're going to talk about horizontal asymptotes. So this is what we would call end behavior. So what happens on the ends? We saw with polynomials that the graphs had, they had end behavior that went up or down on the right and went up or down on the left. For rational functions, we're going to be going toward not infinity, but maybe a horizontal line or a slanted line. So let's just draw a picture here. So we call the line y equals c a horizontal asymptote. So let's draw a picture. Here's y equals c. So this is the point 0, c. So it's the line y equals c. So we call this line a horizontal asymptote if the function goes toward that value as we go toward infinity with our x values. So what this is saying is as the graph goes left or right, f of x goes toward c. So graphically here, we could have our function looks like this, and it's just going to go toward that line, or maybe it looks like this, and it goes toward that line. But eventually, way out here with our x values that are at the extremes, so as we approach infinity with our x values, it's going to look more and more and more like that line, right? Okay, so something that is very commonly misunderstood is that we can cross a horizontal asymptote. So in your mathematical future, it could be that you might explore functions that look like this, right? And that would keep going on and on forever. So it could be that horizontal asymptotes could be crossed, and we'll explore that in a bit as well. So the moral of the story is that horizontal asymptotes can be crossed. On the other hand, vertical asymptotes cannot be crossed, right? Because those came from domain restrictions, didn't they? So if something's not in the domain as an x value, you can't have any ordered pairs that have that x value. So that's why we have, you can't touch the vertical line, right? But horizontal asymptotes, these are not going to come from domain restrictions. Let's see where they come from real quick. So we got the definition. We know what a horizontal asymptote is. Great. So we're going to have a couple of different settings here that we're going to find horizontal or slant asymptotes. We're going to talk about horizontal asymptotes first. So if we have any rational function where, okay, so the leading coefficient of the polynomial polynomial p is a. So let's just draw maybe an example here. So let's say the degree of the numerator is the same as the degree of the denominator. And let's have the leading coefficient be a, and let's have the leading coefficient be b in the denominator. So our function here, f, or I guess r, we're calling it r, doesn't exactly matter. So r is p over q, right? These are both polynomials. And if these have the same degree, let's have a very specific one. Instead of having just in general, let's have specific numbers in here. So 3, maybe x to the third minus 2x squared plus 4. So here's a polynomial of degree 3 in the numerator. I've got a polynomial of degree 3 in the denominator as well. Okay, super. So we want to know what happens as x goes toward infinity. So as our x values get super, super, super large, we want to know what happens to the function. Well, there's a trick here. You're not going to be doing this trick every time in your work. However, this is why we're going to write what we write here. If I take and I multiply both the numerator and the denominator by this value here, we can see what's going to happen. As long as x is not 0, this is an okay thing to do because we can multiply anything by 1, right? Multiplying any number by 1, it's just the same number. So we're multiplying by 1, right? It's just a well-chosen value for 1 that's going to do something convenient, right? Because when we distribute this term here in through the numerator, So it's going to get multiplied by that term, by that term, and by that term. What we're going to get is, well, 3x cubed over x cubed minus 2x squared over x cubed plus 4 over x cubed. And then the denominator, we're going to do the same thing, right? Whoops. We're going to take this same value here and distribute it to this term, this term, this term. Okay, so we're going to have 2x cubed over x cubed minus x squared over x cubed minus 5 over x cubed. Okay, so rewriting this and canceling our common factors, we can have, well, 3, right, because x cubed and x cubed cancel, minus 2 over x plus 4 over x cubed. And then the denominator, we would have 2, and then minus 1 over x minus 5 over x cubed. Okay, so if we're asking what happens to this whole thing as x goes toward infinity, well, what happens to all of these pieces? So this one right here, it only depends on the denominator, right? So if we increase that denominator, we're going to be going toward toward 0 with this piece, right? If I divide 2 by something smaller and smaller, increasingly smaller and smaller, that piece is going to go towards 0, right? So this is going towards 0. This is also going to go towards 0, right? Because the denominator is going to get real, real big. So is that, and so is this. So all these pieces go to 0 except for these two. So as x goes toward infinity, here, our function here goes toward 3 over 2. So this is going to be our horizontal asymptote. So in the general case here, let me erase this. In the general case here, we're going to have something that looks like, you know, a sub n x to the n plus a sub n minus 1, right? Because these are polynomials, right? Blah, blah, blah. And then we've got in the denominator b sub n, x sub n, right? The coefficients that go with the same degree term, right? So if we pulled that trick there, all of these terms are going to go to 0 except for these, and we're left with the original thing, or excuse me, the original just coefficients here, right? So what we're going to write in this little space here is y equal a over b. If these things are the leading coefficients, they're a over b. So maybe I can write that in words real fast. So this thing is the quotient of leading coefficients. So in our work, when we're actually doing these problems, we're not going to do that little trick to say, hey, here's the trick. What we're going to do is just look at it and say, okay, I've got 2x to the 5 minus 3x minus 9 over 7x to the 5 plus 2x minus 3, whatever that stuff is. So if we have the same degree, we just immediately, we say horizontal asymptote is y equal 2 over 7. Just immediately, we say, hey, the degree is the same in the numerator as it is in the denominator. Boom. It's just the quotient of the leading coefficients is our horizontal asymptote, and this is what our graph is going to approach as we go toward the ends, or at the extremes, right? Negative infinity and positive infinity. Okay, so that was if we have the same degree. Now we look at a case where the degree in the numerator is less than the degree in the denominator. So let's look at an easy example. So maybe y equal, I don't know, 2x minus 5 over 3x squared minus 4x plus 5. We can do the same thing. So if I took this guy and I multiplied it by 1 over the highest power of x that appears as a fraction as 1, right? That's 1. If we multiplied that through, isn't the same thing going to happen? We multiply through to here and to here, we're going to get 2 over x. Oops. We're going to get 2 over x minus 5 over x squared. The denominator, we're going to get 3 minus 4 over x plus 5 over x squared. And now we look at all the stuff that's going to go towards 0. So as x, I don't want to be there. As x goes toward infinity, now this piece is going to go towards 0, that piece is going to 0, this piece to 0, this piece is going to 0, right? Because all these all the denominators are going to get really, really, really big. So dividing by something that's really, really, really big is going to get close to 0 real fast, right? So as x goes toward infinity, well, we go toward 0 with all those pieces. So the whole thing, it's going towards 0 over 3, which is 0. So our function, we called it y, is going towards 0. Okay, in general, if we have any leading coefficient at all, so if we did that, like the general case here, blah, 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 and then we're going to have maybe b to the x, or b times some larger power, maybe n plus 1 or something. If we pull that trick, everything in the numerator is going to go to 0, and we're going to be left with one real number in the bottom that's not 0, but the 0 in the numerator is what does it, right? Because 0 divided by any number other than 0 is always 0. So this is always y equals 0. So for example, if I have, y equal 3x squared plus 5x minus 9 over x cubed plus 4x squared, we would just say, all right, what's the degree of the numerator? It's 2. What's the degree of the denominator? It's 3. It's larger in the denominator, so we have horizontal asymptote y equals 0. Every time the degree is less than the denominator, it works out like that. Okay, cool. Okay, so if the degree, we have another case, right? So we had the numerator and the denominator were the same. We had the degree in the numerator is less, and now we're going to have the degree in the numerator is more. This one takes a little bit more doing here. So I think maybe an example is in order. Maybe let's just make one up. So if I have y equal x squared minus 5x plus 2 over x minus 1. So I want to know what happens as x gets really, really big. Well, we can sort of do the same thing that we did with the other examples, but we're not going to. Let's try long division, because this is going to kind of show us what we're going to do. So we know that we can divide this, right? We can either use long division or we can use synthetic division. It might be easier to do synthetic division real fast, right? If I'm dividing by x minus 1, I'm going to put a 1 up there. So we just rifle through this subtraction and multiplication and addition, because we're old pros at this now that we've done it a million times in those previous sections, right? So we bring down our 1, we add, multiply by 1, we add, we multiply, we add, and there we have it. So we can rewrite this as a product of x, we can rewrite it as a quotient and a remainder, right? So our quotient piece is the 1 and the 4, right? 1 and negative 4, so our quotient is x minus 4. And then our remainder, right, this was our quotient. And this is our remainder. So we would have x minus 4, and then plus our remainder, so we would have minus 2 over what we divided by. So our quotient is right there. So now, when we're asking what is going on as x goes toward infinity, well, what we've just shown is that our original rational function can be written like this. Well, where's that piece going? That denominator is going to go toward infinity. So the whole thing is going to go towards 0, right? So this piece here is going to go towards 0. And what you're going to be left with is this thing right here. Well, a way to write that would be, well, y equal the quotient after long division and that is going to be a slant asymptote, right? It's not going to be a horizontal line. In this case here, we found that y equal x minus 4 is a slant asymptote. So just thinking about what this picture is going to look like, we're going to have the line y equal x minus 4 is going to be an asymptote. So our graph is going to approach that line as we approach infinity with our x values. Hopefully when we start putting just all the pieces together all at once, it'll kind of click, because it's sort of weird to talk about each individual feature of the graph individually, right? Because it all goes together. So yeah, as much as we can, let's try to put everything together here as much as we can. So we want all asymptotes. Well, good. That's exactly what we're doing. So we want all asymptotes and all the holes in the graph. Okay, so again with the moral of not moral of the story, but the pro tip, right? We want to factor everything. So we might as well just factor everything right away. So 5x squared, or not square, just 5x. And then the denominator has a square in it, right? Okay. So we can take a look, and what we're going to end up doing eventually is just state what the domain is. So this is x other than plus or minus 1, right? And then we would reduce it. So once we reduce, well, there's nothing to do. No reducing. This means that there are no holes, right? Nothing gets canceled. And further, no reducing meant that both of our domain restrictions are vertical asymptotes. So we got x equal 1, x equal negative 1. So we got two vertical lines that are both vertical asymptotes. And then we would look for horizontal asymptotes. So horizontal asymptotes, we're just looking for the degree. So what we have is we have degree 1 polynomial over degree 2 polynomial. So the degree in the denominator is larger. Every time it's larger, we got y equals 0 is the horizontal asymptote. Done. So we got y equals 0 is a horizontal asymptote, vertical asymptote 1, negative 1, and we do not have we don't have any holes in the graph. Okay, so yeah, try to put it together, see kind of what the picture is going to look like. We're going to have an asymptote at x equal negative 1, excuse me, x equal 1. We're going to have an asymptote at x equal negative 1. And we can start thinking about other points that we should have on the graph, right? Well, I guess y equals 0 is a horizontal asymptote, so that's here. So we got our asymptotes on the graph, and then we should think about other points that we ought to include. Maybe if you put in 0, right, f of 0, that's going to be a horizontal, excuse me, that's going to be a vertical. Gosh, I'm just so into saying horizontal and vertical right now, I guess. I forgot the word intercept. So f of 0, this is going to give you your y-intercept, which in this case is 0. So we got a point right there, right? And now to draw the rest of the graph, we would rely on other stuff we know, right? We just found the only x-intercept as well, didn't we? If we solve where this function is equal to 0, the only place that that's 0 is at x equals 0. So we found the only x-intercept, and we can kind of think about sketching the rest of this graph, because we know it's going to have to either go up there or it's going to go down there, and we can choose which one it is based on a test point, right? Put in 1/2, see what happens. And when we're outside the interval -1 to 1, we could do the same thing too, right? Put a test point in here, put a test point in here. But we're not quite there yet. We're going to put this all together. Maybe we could put it all together in the next example, because this will be a good one. Okay, so we can do it. We want to find all of the asymptotes, all the holes in the graph. So we factor everything. The numerator, we got x minus 2, x plus 2, right? That's the difference of squares. The denominator, we got x minus 2. Okay, so our domain restriction is 2, so we can't have x equal 2. And then we reduce our fraction, right? So x minus 2, those go away. So we've got x plus 2. Okay, so we canceled something, right? So this, we canceled x minus 2. So this tells us that there's a hole in the graph. where x equal 2. This was our canceled domain restriction, right? Because this object here, that's a polynomial and has no domain restrictions. So our graph is going to look like that thing. Well, it's going to be a line, right? But it's going to have a hole in it. Okay, so we want to find horizontal asymptote or slant asymptote. This one might be kind of tricky because didn't we just do division here? So this is the quotient after long division. X plus 2 is the quotient after long division, isn't it? If we would do that, I mean, we definitely can, right? If I put my coefficients here and I put my synthetic division, 1, multiply, add, and lo and behold, hey, there's the quotient right there, right? So we would call that, technically we would call this a slant asymptote. So y equal x plus 2 is a slant asymptote. But if we go and draw the graph, well, the graph of this object looks exactly the same as the graph of this object, except for where x is equal to 2. So we've got, where is that hole? So if we put that in the reduced function, this is 2 plus 2, which is 4. So that tells us that 2 comma 4 is the hole. So we've got points on the line here, x. So drawing this, the function, x plus 2, so that's got y-intercept 0, 2. And we know that the point 2, 4, there's a hole there. But everywhere else, it's going to look like that line. And we're going to call it a slant asymptote as well. So here's the beautiful graph, and it's got a hole in it. Okay, so we found the hole in the graph, we found the domain, we found our slant asymptote. It's going to be kind of weird to call that a slant asymptote because we're used to thinking of asymptotes as things the graph can't touch. But here the slant asymptote is the graph, right? So be careful with this kind of stuff. We're going to have to maybe say uncomfortable things here a little bit in certain cases. But in general, we're going to have them be a little more complicated than this. They're not going to reduce to a linear factor. So, okay, so let's do this one more time here. We got another rational function. We want to find all the asymptotes or holes in the graph. So let's rewrite this. We can factor, can't we? Numerator is going to be what? X. Can we factor that? 2 and 1. I don't think we can. I mean, we can sure find the zeros here, right? Remember when we tried to factor this in the previous section or sections plural? We can use the zeros, right? The zeros of the numerator. We would have that quadratic function or quadratic equation, right? Negative b, so that's negative 4 plus or minus the square root of b squared minus 4 times a, which is 1, times c, which is 2. Okay, whoops. Over, come on now. Okay, over 2 times a, which would be 1 here. So we can simplify that, right? 4 plus or minus the square root of 16 minus 8 would be 8. And then over 2. Okay, so simplifying that, we would have 4 plus or minus, what is this? 2 squared root of 2? Right, because 8 is 4 times 2. Okay, and then we divide by 2, so this is 2 plus or minus square root of 2. So if we really wanted to factor this, we totally could, right? We absolutely can. And we can write it as x minus the first 0, and then x minus the second 0. Okay, so that's the factorization of the numerator. And then this doesn't really factor, right? That's it. So what we have here is that nothing cancels, right? No common factors. So that means that x equal 1 is a vertical asymptote because it's our remaining domain restriction. and we want to know what our horizontal asymptote or slant asymptote is. Well, we look to the degree of our polynomial here, right? So the degree here is 2 in the numerator, and the degree in the denominator is 1. So that means we're going to have a slant asymptote, right? And we're going to need to do we need the coefficient after long division. So we can be tricky, and we can use synthetic division here if we rewrote our denominator here as negative x minus 1, right? We can do that, but let's not be tricky, because we can just use long division here. It's not really that big of a deal. So we got x squared minus 4x plus 2. We're dividing here by negative x plus 1. Okay, so we have to multiply by negative x to get to x squared. We multiply, we subtract. Okay, so negative 4x minus negative x would be plus. Bring down our 2. And then we say, all right, I have to multiply that by 3 to get there. And that's our quotient, right? We've done this a million times before, and we know that that's going to give us our quotient piece. And the piece under here is going to be our remainder, right? But that's not what we're after. We're after that thing, just the quotient. Y equal negative x plus 3 is our slant asymptote. Okay, so we can start thinking of the picture, right? There's no holes, right? Nothing canceled, there's no holes, but we did have x equal 1 as a vertical asymptote. We've got y equal negative x plus 3 is a slant asymptote. Okay, so if we're going to draw the picture here, and we probably should think about it, draw your asymptotes on there. So x equal 1 is a vertical asymptote. And then y equal negative x plus 3 is a slant asymptote. So this is the line that goes through 0, 3, and it's got slope negative 1. So here is another asymptote. Okay. And now what? What else can we put on the graph? Can we put anything else on the graph? Well, if we put in 0, r of 0, right, that would give us 2 over 1. So that's a point on the graph. Super. Are there any other points on the graph that we could put in there? Well, how about these? The zeros of the numerator, 2 plus and minus square root of 2. So wouldn't those be like somewhere in here and somewhere in here? Or are those there? So, I mean, either way, we can put these points on our graph, and we can, make our picture better and better and better and better. And if we're not exactly clear on where to put our points, and I think that they're going to go here and somewhere over here, but that's not exactly the point right now. If we don't know exactly where to put our points, I mean, we can use test points all over the place. Pick something, pick 2, pick negative 1, pick negative 2, and make yourself a more beautiful picture by putting more points on there. We can do a pretty darn good job of drawing pictures with just the little information we have here, right? Because we know that there aren't any other x-intercepts. So that means I'm going to have to approach this line as we go toward infinity with my x's in the negative direction. We know that these 2 points have to connect, and we know that it has to go down because it's not going to go back up, right? Well, and if we had a question of whether or not it does, use a test point, Something else we could do is note the multiplicities of the zeros in the numerator, right? The multiplicity of the 0 meant whether or not it was going to cross or whether or not it was going to change sign, right? So if the multiplicity here is odd, that means it's going to cross right through it. Same with here, right? So I know that there aren't any other x intercepts. So I know that from this point here, going toward the left, we're going to need to approach this line, the vertical asymptote, right? And we also know that it needs to approach that line, the slant asymptote. So, super, super rough sketch, But we got the important stuff on there. We've got x-intercepts, y-intercepts, we got our asymptotes on there, and we have the general end behavior, which is kind of, the whole picture. So, yeah, great. I think that went just fine. So yeah, if you have any questions about anything that went on here, absolutely let me know. Because yeah, we're going to kind of just be snowballing our techniques here and talk about the graphs and draw better and better pictures. So anyway, thanks for watching the video and have a great rest of your day.